Yeah. I would like to talk about my collaboration with John Bell and about the implications it had for me. Where did I meet John Bell? I met John Bell at CERN. It was in 1978 when I moved from Vienna to Geneva to work there for the next years as an Austrian fellow. And CERN at that time was not as big as it is now. There was just this little ring here. I hope you can see it. It was the proton synchrotron, and behind there was the intersecting storage ring. And only in the late 70s and 80s, the SPS ring was built, where the W boson was discovered, and a decade later, the large electron-positron ring. And it is this large electron-positron ring which was reconstructed into the Large Hadron Collider, where recently the Higgs boson has been discovered. Now, my first encounter. I remember very well, it was in one of the first weeks after a CERN theory seminar, where the newcomers have been welcomed and introduced to the CERN staff. And I was standing in the theory common room, holding a glass of tea in my hand, and suddenly an impressive man appeared in the door, fixed me, and approached me immediately. He introduced himself. "I'm John Bell. Who are you?" I was a bit shy and replied, "I'm Reinhold Bertlmann from Vienna, Austria." "What are you working on?" "Quarkonium." And this was already a magic word, since he immediately got interested in, and a vivid discussion started, and we went down to his office, and he was doing some calculations on his blackboard, and so our collaboration started. Now, what is quarkonium? Quarkonium is the bound state of a quark and an antiquark, very much in analogy to positronium. In 1974, a new type of quark was discovered, the charm quarks. And they were produced in the colliders, and these charmed quark and antiquark, they built bound states called charmonium. The bound states and the quarks were already such heavy, about 1.5 GeV, that the non-relativistic Schrödinger equation made sense. The potential used at that time, the favorite potential was a Coulomb potential plus a linear potential. When you put it into the Schrödinger equation, from the Schrödinger equation follow the energy, the bound state, so the masses for the quarkonium, and from the wave function you can calculate the width or the lifetime of the bound state. And in this way, you could calculate, for instance, this charmonium spectrum, which has been measured. So theoretically, you see the potential. This is the potential creating these bound states here. And I must say, remarkably, these bound states approximated rather accurately the measured data. Now, John, as a true Irishman, always drank tea at 4 o'clock. So, 2 minutes to 4, I went to his office. We stepped down to the cafeteria, and he ordered des infusions verveine, s'il vous plaît. Verveine was his favorite tea. And in this verveine atmosphere, we had our discussions about physics, but also about politics. And when Renate, my wife, approached us, we also had hot discussions about modern art. And at home, certainly when we worked in his apartment, we also drank tea. And I remember to choose the right sort of tea was always quite a ceremony. Now, what was our approach actually to calculate these bound states? We relied on ideas coming from quantum field theory. And in quantum field theory, you have as a first, or I would say zero approximation, a free quark-antiquark pair. This corresponds to this first graph here. This is a Feynman diagram. And in order to account for the short distance interaction, you have to include the gluon propagator, second diagram. Now, but to feel now the longer distances, the confinement part, we took up an idea of a Russian group who proposed the following. This heavy quark-antiquark pair is placed in a vacuum, and the physical vacuum is the QCT vacuum. And in a first approximation, the QCT vacuum consists of soft gluon fluctuations. And these soft gluon fluctuations are here and are called gluon condensate. And when you calculate all these diagrams, this is a vacuum polarization tensor. And then we also made a non-relativistic limit here, this quantity, and we averaged it with such an exponential. And this average is called by mathematicians a moment. This tau here is a free parameter, and it is actually an imaginary time. And now we observe the following, which amazed us very much. This tau, this imaginary time, produces the moment with this imaginary time produces a balance, somehow a magic balance between the perturbation theory and the confinement. That means the time is small enough for the perturbation theory to be valid, but also large enough to feel the confinement property. And when you calculate from these moments what you can do, the ground states, it turns out that they are nearly exact. And this was really a great surprise to us. And we just named our paper Magic Moments. Yeah, we also tried to attach to this third diagram so to say, the confining part, the first approximation to the confining part. We tried to attach a potential. It turned out that the potential proportional to this gluon condensate term goes with r to the fourth and is proportional to the quark mass. So that means this potential here is rather steep and mass, so flavor dependent. This, however, is very much in contrast to the potentials which have been used by, I would say, the effective potential builders. They used in their calculations a potential which was rather flat and mass independent. So we did not find a bridge between our ideas from quantum field theory and the effective potential models. Yeah, and now I would like to say something about John and Mary as a couple in science. John, for me, was the physicist. He was not only a quantum physicist, as you know him, but he also was a highly respected particle physicist, and he also was an accelerator physicist. and Mary is an accelerator physicist. So there was a scientific connection between both. Let me start with John being a particle physicist. In particle physics, John Bell has done really fundamental works, starting already with his PhD. His PhD in the middle of the 50s was about time reversal in field theory. And there he proved nothing but the CPT theorem. And the CPT theorem is, as you know, the mirror image of our universe. And we all believe that this CPT symmetry holds for our known interactions. Now, the most quoted paper, I think several thousand times in this field, is his paper about the anomaly in quantum field theory. The anomaly in quantum field theory means there is a breakdown of a classical symmetry due to quantum effects. And this effect, this anomaly, is responsible for the decay of a pi0 into two gammas. He did this work together with a postdoc at that time with Roman Sharkiv, and quite independently also Stephen Adler from Princeton clarified this phenomenon. And in this case, the axial current is not conserved in a massless limit, but is proportional a term called the anomaly. F mu is the field strength tensor. And this is precisely the term which produces the transition from the pi0 to the two gammas. I just want to tell you the anomalies are really very, very important in quantum field theory. They occur in gauge theories. They also occur in gravitation. And they are such important because they restrict your theory. Let me finally mention also important work he has done together with De Raphael about the muon anomalous magnetic moment, and with Llewellyn Smith, the later CERN general director, about neutrino reactions. Yeah, now John is an accelerator physicist. John came to Harvard, to the Atomic Energy Research Establishment in the 50s. And he stayed for a short time in Malvern, and he received his PhD at the University of Birmingham. And here you see John at Harvard in 1952 riding his new Ariel. And Ariel was a very popular motorcycle at that time. At Harvard, John has written papers about accelerators beside his work on nuclear and particle physics. He also has written accelerator papers when he was later on at CERN together with Mary. I will come to that separately. And he also investigated the Unruh effect. The Unruh effect, for the Unruh effect, his idea was to use the accelerated electrons as a detector to measure the black body radiation of the Unruh vacuum. Yeah? And the papers appeared together with Jon Linus, and the result was that there is a depolarization of the spin of the electrons due to the acceleration in the Unruh vacuum. Yeah? The effect, however, is small but measurable. Yeah, now I would like to come to Mary. Mary is an accelerator physicist. She graduated 1947 from the Glasgow University and moved immediately afterwards to Harvard in the theory division. And at that time, the head of the theory division was a certain Mr. Klaus Fuchs, who is, I think, well known to the older generation. In 1949, Mary and John met at Harvard, and 1954 they married. And in 1960, Mary and John moved to CERN. John to the theory division and Mary into the accelerator research group. Mary has written several papers at Harvard in the 50s, and mainly about how to focus, how to stabilize the beams in an accelerator. And I think at that time it was quite a hard job, because at that time there didn't exist these great computers what we have now. So you also had to do many computations with your hands. And she also investigated and published papers at CERN. They're mainly about electron cooling. And now the work Mary and John, what they did together. In the late 70s, the big question was how to stabilize the beams in the accelerators. There were essentially two methods. One method was electron cooling invented by Budker in Novosibirsk, which was quite successful, and the other was stochastic cooling, invented by Simon van der Meer at CERN. He got the Nobel Prize for it. And stochastic cooling was used, for instance, for the SPS ring. John and Mary, however, they investigated electron cooling. And that is something I also want to mention. One paper they dedicated to Yuri Orlov. And Yuri Orlov was an accelerator physicist who also was fighting for human rights. And for that reason, he was imprisoned in the Soviet Union for many years. Later on, because of such a campaign, he became free. Yeah, then they also worked together in the field of quantum Beamstrahlung and quantum Bremsstrahlung. Yeah, and here you see a young couple having picnic at Stonehenge in the 50s. Yeah, and now I must drink a glass of water. Now I have to tell what happened to me. It was in 1980 when I visited my home institute here in Vienna. And at that time, there was certainly no internet, no archives, but we had a rather efficient system of sending preprints of the new works we did in order to inform the community. And the person who was responsible at our institute for receiving the preprint and distributing them on a shelf was my friend Gerhard Ecker. I think he is here somewhere. Yeah, here he is. He is the witness for what I tell now. Yeah. I also remember I was sitting in that computer room, typing my calculations into the computer, as suddenly the door opened and he appeared, waving a preprint in his hand, and he shouted, "Reinhold, look what I have here." Then I looked, and I have seen the name in the title of my preprint. Then he opened it and has shown me a cartoon which resembled very much myself. So you can imagine I was totally excited. And it was this paper of John Bell about Bertlmann's socks and the nature of reality. Then I was reading the first paragraph, and when I have read this, you can imagine my heart stood still. Since John compared habits of myself to wear different socks with the EPR phenomenon. And he even asked the question, provocative, isn't the EPR business just the same? But as we know, no. And in this paper, he discussed in a very witty way why this is not so. And it was only after this paper that I got to know John's quantum work. And nobody at CERN, I had to study it really for my own. Nobody at CERN could explain me exactly what it was. It was even worse. Nobody at the time was interested in. After studying it, I also wanted to take revenge, and I tried to take revenge in a paper I devoted to him in 1988 on occasion of his 60th birthday. I wanted to educate the particle physicists, but I totally failed. However, on my last page, I made the conclusions. And the conclusions, for the conclusions, I have drawn a cartoon where the spooky ghost responsible for the non-locality comes out of a Bell whiskey bottle, which really does exist. And this John, being a real realist, enjoyed very much. Yeah, now the implications it had for my life. You can imagine, after this paper, I was immediately, instantaneously pushed into the quantum debate. And it had real deep implications for my life and also for my research. About my research. I met Anton Zeilinger in the beginning of the 90s, and there we thought we have to educate the young students. And we founded a joint seminar where his group from Innsbruck was coming to Vienna, giving talks about their experiments, and the Viennese students traveled to Innsbruck, seeing his experiments and laboratories. And in 2000, when he moved from Innsbruck to Vienna, we organized our first Quantum Unspeakable conference, where many of you already attended. Yeah, also in the 90s, I realized that these features, these entanglement features, occur also in particle physics. They occur somehow automatically when in an accelerator a particle and an antiparticle is created, produced. They are automatically entangled. And I was very lucky to find excellent and enthusiastic students. In a whole series of papers, we investigated several systems, the strange systems, so the kaon, anti-kaon systems. We also studied entanglement of beauty, so the B-meson systems, and so on. And in the later years, I also got interested in relativistic entanglement. There we studied when the observers are moving relativistically or even are very much accelerated, which resembles somehow a black hole situation. You can calculate then what happens there. Yeah. Again, I was lucky to collaborate with the mathematical physicists Walter Thierry and Heidi Nannhofer, and I just want to mention one feature which I find remarkable, that is, when you consider an entanglement witness inequality, the violation of this entanglement witness inequality for a given entangled state, this amount of violation is equal to the Hilbert-Schmidt distance of that state to the set of separable states. Yeah? Yeah, and finally, I come back to John Bell as a quantum physicist. What is the main points for me, the main questions? In his first paper about the hidden variable theory, I must say I was very much impressed by his moral strength to criticize von Neumann. Von Neumann incorrectly assumed for his proof on hidden variable theories that in a hidden variable theory, this additivity of expectation values of operators is valid. It is valid in quantum mechanics, but for states which are further characterized with a parameter with a hidden variable, these states are called dispersion-free. It does not hold. And John gave counterexamples. He proved this in what he called a corollary. So the additivity does not, of expectation values, does not hold for dispersion-free states. By the way, this also could be inferred from Gleason's theorem. And John said why, also explained why, there are 3 different settings, and these may depend, will depend on the disposition of the apparatus. And this is what we nowadays call contextuality. And indeed, in 1967, Cochin and Specker proved their theorem that non-contextual hidden variable theories are incompatible with quantum mechanics. The second issue is non-locality, and this was a very important issue for John, I must say. I would like to quote him. John said, "It may be that we have to admit that causal influences do go faster than light. The role of Lorentz invariance in a completed theory would then be very problematic." And I remember this puzzled John, being also a quantum field theorist, who certainly would like to have Lorentz invariance. This puzzled him very much until the end, I think. And now I come to his last paper, which he called La Nouvelle Cuisine. And this paper is also written in his typical, as Mermin called it, literary style. So if you read it, it is just very enjoyable. And this paper relies on a talk he gave in 1988 at the University of Hamburg. And his title was, "What cannot go faster than light?" And a person with Hanseatic humor added by hand John Bell, for example. But this made John thinking. what does this person mean? Does this person mean my whole body cannot go faster than light? Or just my legs, my cells, my molecules, the atoms, or the electrons? Is it meant that none of the electrons go faster than light? And nowadays, in our modern view of nature, we know that the sharp location of an object dissolves. It dissolves non-relativistically by the fuzziness of the wave function and relativistically by the fluctuations of a quantum field theory. And finally, John stated the concept of velocity of an electron is nowadays unproblematic only when not thought about it. And this I like very much. And at the very end, I would like to let him speak by himself.
Oh, I'm a realist. And I think that idealism is a kind of, I think it's an artificial position which scientists fall into when they discuss the meaning of their subject and they find that they don't know what it means. I think that in actual daily practice, all scientists are realists. They believe the world is really there, that it is not a creation of their mind. They feel that there are things there to be discovered, not a world to be invented, but a world to be discovered. So I think that realism is a natural position for a scientist. And in this debate about the meaning of quantum mechanics, I do not know of any good arguments against realism.
Yeah. Thank you very much for your attention. You might have liked it.
Thank you very much. We have time for some questions, if there are some. Comments?
Yes, please. Bertlmann.
If before going home every day you'll go to a laboratory and ask students to make an EPR experiment and put your socks for tomorrow according to these results, then the Bell's paper will not be correct?
We have to check. Is there another question? The final, I will give the final answer. As a final.
Yesterday, your left sock was pink.
Okay, okay. So I cannot escape. Okay. So So you want to see the socks of today, the color of today, yeah. Also, now, linkes Bein. Can you see? And now, what is your choice?
Red. Not green. Pink.
Not rechtes Bein. So, blue was a good choice. Yeah. Okay. Thank you very much.